Now students, we'll take up our next topic, that is cell representation. How the cell is represented. See what we find in cell. We find that one anode is there, cathode is there, and in between salt bridge is there. So for salt bridge we draw parallel lines. Here we'll write anodic reactions. Here we write cathodic reactions. Let us take example of Daniel cell. Zn oblique Zn2 plus salt bridge copper 2 plus oblique copper 0. Concentration of the electrolyte is taken as 1 molar. With the help of this cell representation, what we understand everything, that if you prepare a cell where Zn will be getting oxidized, Zn giving us Zn2 plus, and copper will be getting reduced, copper 2 plus giving me 0, and the concentration of both the electrolytes are 1 molar. So this is the way you represent a cell. Now class, next question comes that if we change the concentration of the electrolyte, what is going to happen on the EMF of the cell? And for that, Nernst equation came into existence. So, dependence of electrolytes, dependence of EMF on concentration of electrolytes, and that is given by Nernst equation. What is the Nernst equation? E cell equal to E0 cell minus 0.059 upon N log product upon reactant. So this is basic Nernst equation. Let us understand the entire thing again. E cell is the EMF generated at any given concentration of the electrolyte. I repeat again, E cell is EMF generated by cell at any given concentration of the electrolyte. E0 cell or E0 cell, that was your standard EMF. And number of moles of electron taking part, and P is your product, R is your reactant. That will I make understand while we'll go for a numeral. Class, I repeat Nernst equation again. E cell, that is the EMF of the cell at any given electrolyte, at any given concentration of the electrolyte. E0 cell under standard condition, that is standard EMF, 0.059 upon N, and is the number of moles of electron taking part. Number of moles of electron taking part, and P represents product and R represents reactant. And don't forget what this square bracket represents. Square bracket represents molar concentration. Class, one thing more. If I write here copper 0, square bracket represents molar concentration. Copper 0 means what? Copper solid. And remember your chemical equilibrium. Actually, class, it is your P by R. It is coming from chemical equilibrium. That is your law of mass action. We are not undergoing Loma expressions. So, what concentration we have taken for solid species? Remember, it was 1 only. So, during cell reaction, if I get anywhere copper 0 or any metal having 0 charge, it means it is in its solid state, and the solid state concentration is always taken as 1 molar. So class, let's have a numerical based on this. Calculate E cell, and it has been given to you Zn oblique Zn2 plus salt bridge Ag plus oblique Ag0. Here concentration is given 0.01 molar. Here it is given 0.1 molar, or you can take 0.001 molar. and some data has been given to you. Reduction potential of Zn2 plus oblique Zn0 minus 0.76 volt, and E0, the reduction potential of silver is 0.80 volts positive. So class, remember your cell theory. Higher the reduction potential, more the tendency to get reduced at cathode. So, which has more reduction potential? Silver has more reduction potential. So, silver will undergo reduction and Zn will undergo oxidation. Concentration of electrolytes already given to you. So, what you have to do, you have to write anodic and cathodic cell reaction first. Anodic reaction, remember, I have been telling you from very beginning, oxidation takes place at anode. So, who is going to oxidize at anode? Zn is getting oxidized at anode, and this is the reaction. Class, remember, the reaction has already been shown over here. So, Zn was the initial state, Zn2 plus was the final state, and since oxidation is taking place, change by 2 electrons, so I will write here 2 electrons. Similarly, reduction of silver taking place, cathodic reaction, reduction, Ag plus 1 electron gives me Ag0. This is a cathodic reaction. But class, you all know that number of electrons should be same. Zn is giving us 2 electrons and silver is consuming only 1 electron. So what we'll have to do? We'll have to multiply this reaction by 2, cross multiply, and this reaction by 1 to balance total number of electrons. So I can write Zn giving me Zn2 plus 2 electron, 2 Ag plus consuming 2 electron, giving me 2 Ag0. So by adding, just add 2 electron gets cancelled, and I get my value Zn plus 2 Ag plus giving me 2 Ag0 plus Zn2 plus. So class, this is the overall cell reaction. We'll have to undergo all these steps. The reason is that if you want to put it in Nernst equation, I should know what are my products and what are my reactions. So in the next step, I am just going to first calculate E0 cell, because I require E0 cell here and I know very well 2 electron sinking part. PYR, I'll just make you understand. So E0 cell was E0 cathode minus E0 anode. Cathode is your silver with reduction potential value 0.80. Anode, reduction potential value plus. Remember it, though Zn is going for oxidation, still will, while calculating M of the cell, will take reduction potential values. Add it, I get positive 1.56 volt. Since the E0 cell is positive, it means the cell reaction is spontaneous. Putting the value in Nernst equation, E cell equal to E0 cell 1.56 minus 0.059 upon N, and is 2 log product. These are the products. So Zn2 plus square bracket multiplied class, remember no plus here, multiplied by Ag0. This is your Loma expression upon stoichiometry is 2, so whole square. Then Zn multiplied by Ag plus whole square, because stoichiometry is 2 over here. Now we'll just put the value and solve the equation. 1.56 minus this gives you 0.0295 log. Class, this is solid, again value 1, again solid, value 1, so you have to write only these two values. So Zn2 plus 10 to the power minus 2 upon Ag plus ka whole square, it is 10 to the power minus 3. Ka whole square will give you 10 to the power minus 6. So 10 to the power minus 2 divided by 10 to the power minus 6 gives you minus 4 here. It goes up, gives you log 10 to the power 4. Log 10 to the power 4. And class log 10 to the power 4 has value 4. So 1.56 minus 0.0295 multiplied by 4. So let's find out the value. .0295 multiplied by 4 gives you 0.118. So I'll subtract 0.118, 0.118. Right, so I get my value 1.442 volts. So class, this is the way you can solve your Nernst equation. And since I've already taken Nernst equation, we have solved a numerical over here. Now I give you one homework to solve in your fair register. So I'm writing more now. Solve only on this numerical. Okay, value I am giving you by own. Please don't quote. You are supposed to understand the steps. Given E0 aluminum 3 plus oblique aluminum 0 minus 0.80 and E0 copper 2 plus oblique copper 0 is positive 0.34 volts. Class, do as homework in your assignment. Note it down. Now class, we'll take up next topic, that is relation between delta G, that is your free energy change, and EMF of the cell. Delta G0 equals to minus NFE0 cell, or delta G equal to minus NFE cell. Both are same expression, only the first one contains 0 over here, it means standard state. If I am putting standard over EMF over here, we'll get my standard value of delta G. If I am putting any other value of EMF over here at any given condition, that I'll get my free energy change at any given condition. Class, let's solve a numerical over here. Calculate delta G0 for following Daniell cell reaction. The same reaction giving you copper 0 and 102 plus. Class, one thing more. N is your number of moles of electron taking part, and F is your Faraday's constant. Faraday's constant. And since it's a constant, it is a value always fixed, 96,500 coulombs. Class, we all know that number of electrons taking part is very well being observed over here. Zn is giving 2 and copper is consuming 2. So N is 2, Faraday is 96,500 and E0 cell has been also given to you 1.10 volt, and if it is not given, then reduction potential value will be given to you. You can very well calculate it. So E0 cell is 1.10 volt. I'll use my standard conditions. Delta G0 equals to minus NF E0 cell. Number of moles of electron 2, Faraday constant 96,500 multiplied by 1.10 volt. So we get total value over here. (212,300) joule per mole or 212.3 kJ per mole. Class, quite often this question is asked in your board examination. Nernst equation, this equation, these are very, very important. Class, when next time we'll meet, we'll work on relation between EMF of cell and equilibrium constant Kc. We'll take up our in the next class. Relation between E0 cell and equilibrium constant that we studied in class 11 Kc. Class, you know, at equilibrium EMF generated by the cell is 0. So putting the value in Nernst equation, which was E cell equals to E0 cell minus 0.059 upon N log Kc. Class, remember we used to write log P by R, and P by R was your Loma expression. So in place of P by R, we can very well write Kc. Now putting the value of E cell here, we get 0. E0 cell minus 0.059 upon N log Kc. E0 cell is brought here. So negative get positive. So we ultimately get E0 cell equal to 0.059 upon N log Kc. So this is the expression for E0 cell and Kc. Class, this thing is very, very important because this was asked in 2020 board examinations. Class, I have a numerical on this. Calculate Kc for Daniell cell if E0 cell equals to 1.10 volt. Plus, reaction is given. We all know that Zn is getting to oxidize and copper is going to be reduced. So number of electron taking part is N equals to 2. So putting the value here, so E0 cell equals to 0.059 upon N log Kc. E0 cell is 1.10, 0.059 upon 2 log Kc. Multiply, you get 2.20 upon 0.059 equals to log Kc. Class, that gives me 37. If you solve 2.20 upon 0.059 equals to log Kc, we get final value here 37.28 equals to log Kc. Now in the next step, multiplying both sides by antilog. If you multiply, you get 37.28 anti-log 37.28 equals to Kc. Class, the value will be 37 will become the power, and if you go through anti-log table, 0.28, the value comes 1.9. So ultimately, we get the value of Kc 1.9 into 10 to the power 37. So this is the way you can solve your numerical of E0 cell and equilibrium constants. Commercial cells, there are two types, primary cell and secondary cells. What is basic difference between them? Primary cells are non-rechargeable cells. You cannot recharge them. Example is your Lee-Klinke cell. Secondary cells are always rechargeable cells. Example, lead accumulator cells. So class, we are going to take up first Lee-Klinke cell. This cell is also called battery, which we use in our radio and torch. How it is made up of? See, in middle you get a graphite rod which acts as cathode, hence positively charged. Then the container, the case, is made up of zinc. It is a node, acting as a node, negatively charged. In the next compartment, MnO2 plus carbon paste is there. I repeat, MnO2 and carbon paste. And the next compartment, it is filled with ammonium chloride to make the medium basic. So class, what is going to happen? At anode, zinc is getting oxidized from Zn to Zn2 plus, liberating 2 electrons. And at cathode, MnO2 plus ammonium plus 1 electron, reduction taking place, and it is giving me, it is called basic manganese oxide, MnOH plus ammonia. So this is anodic reaction, this one is cathodic reaction. Cell output, it is 1.5 volt, and we use in radio and torch. So class, this was your Lee-Klinke cell. I repeat again, cathode is made up of graphite rod, anode is made up of zinc case, and this graphite rod is surrounded by MnO2 plus carbon paste, and which is further surrounded by ammonium chloride. Anode, Zn getting oxidized to Zn2 plus 2 electron, and at cathode, MnO2 reacting with ammonium plus 1 electron, giving me basic MnOH plus ammonium. This was your Lee-Klinke cell. Now class, we'll move to lead accumulator cell, that is your rechargeable cell, secondary cells. See, here anode and cathode are made up of, see, anode, negative charge made up of lead rod. See, lead, 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 lead. So they are connected in series. So that constitutes negative plate. And then cathode is made up of PbO2, 1, 2, 3, 4, all again connected in series. That is your positive plate working as cathode. This is your negative plate working as anode. Now both the rods are dipped in 38% sulfuric acid by mass. That is your electrolyte over here. Cell reaction at anode, Pb, that is your lead, in presence of sulfate gives us PbSO4 liberating 2 electrons and hence oxidation taking place. At cathode, PbO2 plus 4H positive plus sulfate plus 2 electron giving me PbSO4 plus twice H2O. So class, here you see lead is at 0 state, here lead plus 2, 0 plus C, 0, from 0 it is moving to plus 2, so oxidation of lead is taking place. Then in PbO2, here you see minus 2 into 2 minus 4, so oxidation number of lead is plus 4, and here plus 2, so from plus 4 to plus 2, so reduction taking place, so Pb is getting oxidized and PbO2 is getting reduced. So at both the reaction, you get a final reaction Pb plus PbO2 plus twice H2O4 giving me 2 PbSO4 plus twice H2O. So cell output is 1.5 volt per plate. Plus, this is your rechargeable cell. What happens during functioning of the cell? You see sulfuric acid getting consumed. You see sulfate ion, 4H positive ion. So the density of sulfuric acid start falling, and when the density of sulfuric acid starts falling, then cell requires recharging. So in the next topic, we are going to discuss recharging of a cell, that is your secondary cell, and that is lead accumulator cell. that is your recharging of secondary cell, and that is your lead accumulator cell, the same cell which we have discussed just now. So when the density of sulfuric acid, I repeat, and you note it down, the density of sulfuric acid start decreasing by 38% sulfuric acid by mass, then cell requires recharging, and during recharging of the cell, a higher current is flown in the opposite direction where opposite cell reaction takes place. The same reaction, I am going to reverse it. 2 PbO2 plus twice H2O is going to give me Pb plus PbO2 plus twice H2, so forth. So during recharging of the cell, reverse reaction takes place, and ultimately your sulfuric acid is regenerated and your cell starts functioning again. So that is the recharging of lead accumulator cells. Fuel cell. The basic preparation of fuel cell is that there are two graphite porous electrodes, small pores are there, and in between alkaline solution, that is NaOH is filled, and this is your negative plate and this becomes your positive plate. In anodic compartment, hydrogen gas is fed, and in cathodic compartment, O2 gas is fed. So I repeat again, fuel cell, in between, in the middle, you find alkaline solution NaOH surrounded by two graphite porous electrodes having small pores, because these gases will go inside this, and in the next compartment we are feeding hydrogen gas in anodic compartment and oxygen gas in cathodic compartment. The reaction taking place: anode, hydrogen gas in presence of alkaline solution forming water, liberating 4 electrons. At cathode, oxygen getting reduced, O2 plus twice H2O, consuming 4 electron, giving me 4 hydroxyl. If we add both the reaction, 4 hydroxyl goes with 4 hydroxyl and 2 water goes with 4 water, leaving 2 water. So the overall net cell reaction is twice H2 plus O2, giving me twice H2O. What are the advantages of fuel cell? Plus, fuel cells are highly efficient. Other commercial cells, they have efficiency ranging to 40 to 60%, but fuel cell, they give you efficiency of 70%. Secondly, non-pollutant. Byproduct is simply water, and you all know that water is non-pollutant. And third is continuous source of energy. Till you are feeding hydrogen and oxygen gas in the chamber, the electricity can be obtained. So that is continuous source of energy, and it is used in space rockets. Class, we come down to our last topic of electrochemistry, that is called corrosion. So how do we define corrosion? It is deterioration of metal surface by layer in presence of moisture and air, is called corrosion, and in case of iron it is called rusting. So rusting of iron is in your syllabus that we are going to pick up now. Corrosion. See, when iron metal surface is left exposed to air, then small galvanic cells get set up. Galvanic cell means simply electrochemical cell where you find anode, cathode and electrolytes. So class, pure iron surface acts as anode. Cathodes are impurities. What are impurities? Other metals. Electrolytes, moisture, water. Then you know in atmosphere CO2 is also present and O2 is also present. Plus this CO2 and H2O reacts to give us carbonic acid, and that S positive is utilized during cathodic reaction. So class, let us first see what is happening at anode. Pure iron surface get oxidized to Fe2 plus, liberating 2 electron, and at cathode oxygen get reduced in presence of H plus ion, which we get by combination of H2O plus CO2 giving me carbonic acid. So H plus ion will be liberated there, and in presence of 4 electron, it gets reduced to twice H2O. So in the first step, iron getting oxidized to Fe plus 2. Now when the Fe plus 2 is already present on the surface, then in presence of air, Fe plus 2 get oxidized to Fe plus 3 in presence of air. So twice Fe2 plus twice H2O plus half O2 will give you Fe2O3 plus 4H positive. So now you see that ferrous ion has been converted to ferric ion, and this Fe2O3 will react with water to give us rust, and formula for the rust is Fe2O3 dot XH2O. So how to prevent rusting of iron? How to prevent? Number one, by barrier. What are barriers? If we paint the surface by paints, varnish, so they act as a hindrance. Varnish, so they act as a hindrance, and hence they stop corrosion or rusting of iron. Number two, by electrical methods. This is an iron plate, or iron pipe connected with more active metals such as magnesium. So these iron pipes are found in the sewer lines. So if these iron pipes are connected with a wire with the help of more active metal, that is magnesium, what happens? Magnesium gets oxidized in preference to iron, and hence no corrosion of iron will take place. Number three, galvanization, that has been studying from class 10. So iron and Zn are mixed to get galvanized iron pipes. Galvanized iron pipes. We all know that Zn is more reactive than iron, therefore Zn gets oxidized in preference to iron, and hence again hindering the process of corrosion. So class, so that was the last topic of electrochemistry. We have studied entire electrochemistry in 3 topics: electrolysis, electrolytic conductance, and electrochemical cells. And this completes my entire electrochemistry chapter.